Good evening, and thank you for joining us for our 11th annual John R. Mother Visiting Scholars Lecture. I am Estella Atekwana. I'm the Dean of the College of Earth, Ocean, and Environment, which is home to the Department of Geography and Spatial Sciences, host of tonight's lecture. The department has changed its name since John Mather, known as Ross, led it years ago, reflecting an increasing focus on data science and using the tools of geography, like remote sensing, geographic information systems, and environmental data analytics to investigate and solve problems in both the environment and human society. But the study of the atmosphere, meteorology, and climatology are still central to the work of scientists in the department, and their cutting-edge research on our climate will be familiar and celebrated by Ross. Ross was deeply committed to University of Delaware, to his department, to the faculty, students, and staff who were its heart. He was a professor in the Department of Geography for 40 years and chaired the department for 23 of those years. He influenced generations through his work as a researcher, as a professor, and as an administrator. As stated by one of the alums from the geography department during my recent conversation, Ross had the ability to take complex things and make them simple. Ross left a legacy that lives on today. This lecture series was established by his wife, Dr. Sandra Mather. It seeks to honor his memory and continue his legacy by fostering the ongoing discussion of ideas in the field to which they have both devoted their lives. We are grateful to Sandy for her generosity. So thank you, Sandy. At the University of Delaware College of Earth, Ocean, and Environment, we work every day to connect our science with society, to find ways to serve our community with our research, and to drive innovation, both through the work that happens here and through the graduates we send out into the world. Ross had a similar respect for conducting science that would have real world benefits. And our speaker for the Mother Lecture today is a leader in public engagement around climate and weather science. It is now my pleasure to recognize Professor Tracy Deliberty, the interim chair of the Department of Geography and Spatial Sciences, to introduce our speaker.
I'm thrilled to get a chance to say a few words about Dr. John Russ Mather and his lectureship, and to introduce our distinguished speaker. This lecture, as Estella has stated, is in honor of the memory of Russ Mather, professor of the Geography Department from 1963 to 2003. This lectureship was established by Dr. Sandra Mather in honor of her husband, and able to bring these scholars to the department. We have lots of registers. 268 guests were registered for this event, which is just amazing. Russ would be smiling down on us, and Sandy, I'm sure, is thrilled, is in the audience today with this attendance. Russ became a blue hen, like I said, in 1963, when he was hired as a full professor in deference to all his research contributions that he had had up to that point. He served in the chair of our department for 24 years. I cannot imagine that, and played a big role in the development of our initial department and in our climatology PhD program. So let's turn our attention to our speaker tonight. It's my pleasure to introduce our speaker, Dr. J. Marshall Shepard. He's a full professor residing in the Department of Geography at the University of Georgia. He carries the title of Georgia Athletic Association's Distinguished Professor of Geography and Atmospheric Sciences. His research focuses on hydrometeorological extremes, urban climate, and the intersections of atmospheric science with society. He uses remote sensing, weather and climate models, and risk vulnerability approaches to address challenges of things like urban flooding, energy, food, water nexus, weather climate risks, and communication warnings. Dr. Shepard holds and has held key leadership positions. He was the president of the American Meteorological Society in 2013, presently serves as the chair of NASA's Earth Science Advisory Committee, and interesting, some of the other things he does is hosting the Weather's Channel Sunday talk show called Weather Geeks. In all his spare time, back at his home institution, he also is the director of the Atmospheric Sciences program. Dr. Shepard has earned numerous awards. In 2018, he was a recipient of the AMS Helmut Landsberg Award for his pioneering and significant work in urban climate. And an year earlier, he was honored again by the AMS with the Brooks Award, a high honor within the field of meteorology. In 2015, Dr. Shepard was a recipient of the Association of American Geographers Media Achievement Award. He also has a TEDx Atlantic talk called Slaying Climate Zombies. That would be fun to talk with him more about that, which is one of the most viewed climate lectures on YouTube. He has over 90 peer-reviewed scholarly publications, books, which is just amazing, some chapters in books, and numerous articles. It's always fun to kind of look at what the most current one that he recently submitted was with the Journal of Southern Hemisphere Earth System Science, was looking at doing a case study on the analysis of Cyclone Kelvin. Dr. Shepard has attracted more than $3 million in external funds. Two of his current ones are very interesting. A current grant looking at assessing Georgia's water resources using satellite data and novel precipitation metrics with the Department of Interior. And he's also working on a really interesting new NASA grant to study the impact of surface moisture on tropical cyclones, re-intensification over land. With that, I'll let Dr. Shepard introduce his title of his talk and go ahead.
Well, thank you very much, Tracy, and to the Dean for those kind remarks. And I want to thank anyone, particularly Dr. Mather's spouse, for establishing this lecture series in his honor. I know it extends his legacy quite a bit, and I'm just happy to play a small part in that. So thank you all for the invitation. Thank you, Del Levia, who I assume is on as well. Like me, I heard he was having some trouble getting on, as did I earlier as well. I want to give a shout out to some people. I've had some affiliations with the University of Delaware program for some time. My colleague here at the University of Georgia, Dr. Andy Grunstein, I know many of you know. I know Dan Leathers is a professor that he worked with, and I just learned, Tracy, that you were on his committee as well. So it's really neat to hear that. So, and we just recently graduated one of your recent alum, Miss Margaret Orr, who's now a graduate student at George Mason, but was an outstanding master's student here at the University of Georgia, one of my favorite students. So thank you for sending her along from the University of Delaware. It was quite awesome. So I'm going to share my screen and we'll get started here. So bear with me for one moment. Okay, so can everyone see a screen that looks like the city of Atlanta and my name? Very good. So I am going to talk to you today about the science of how cities affect rainfall and storms. This is an area of study that I have immersed myself in for almost 20, I guess a little over 20 years now, perhaps. As it said in the title of my flyer for this talk, I was honored to receive an early award from the President George Bush at the White House in 2004 for work in this area. Early Career Award. And so just really extended this work during my career at NASA. I spent 12 years at NASA's Goddard Space Flight Center before joining the faculty at the University of Georgia in 2005 now. Wow. So it's been quite a while. So I want to kind of give you the context, because what you're looking at there is from an airplane at the city of Atlanta. That's the core central business district of Atlanta. And you see a low-level cloud deck. But you also see an opening in that cloud deck where the warming of the Peachtree Road corridor is. So you have this urban heating that's interacting with the lower atmosphere. And so that is sort of an underlying premise of the talk today, how this environment, these urban spaces, these cities can impact rainfall, storms, and flooding. So there you see my coordinates. Let me briefly explain this Georgia Athletic Association Distinguished Professor, because I get questions about it all the time. I don't study athletics, kinesiology, exercise science. Our athletic association at the University of Georgia is quite successful and is its own entity. And so, like, you might have the IBM professor of computer science or the Coca-Cola professor of business. Our athletic association has several endowed professorships. They're quite attractive ones, that some of its more productive faculty on the campus can be put up or nominated for. So it's just an endowment. It's an endowed professor chair, just like many of the others that I mentioned. So, and for those of you that are listening tonight and are on Twitter, Twitter is there at Dr. Shepard 2013. For those of you in social media, you know I'm active in social media. So happy to join me on Twitter. Feel free to tweet my talk if you want to. I'd love to retweet you. So I want to start off with a couple of what if questions, because when I do science, again, my pedigree and my lineage is not academia. I kind of sometimes call myself the anti-academic in the sense that I come at things, I didn't come at things in the traditional pathway of an academic, graduate school, doctorate, postdoc, faculty position. I spent quite a bit of time at NASA for 12 years doing mission-related climate work and then doing some policy-related work. So my work is often driven by a so what factor. I do theoretical research too, but I'm always interested in the so what's. And so I want to pose these questions. What if you could plan or design cities to strategically leverage rainfall? What if a system of urban spaces amplified effects on weather? And I just see a typo there. I need to correct that on the future version of the talk. And what if cities were making flooding worse? I think we know that that happens. And what if there was less freezing rain in urban areas? These are questions that I am going to deal with in the talk today, because oftentimes when people think about urban climate, it's just the urban heat island. And the urban heat island is very well studied. We know a lot about the urban heat island. But my work centers around urban hydrometeorological processes, rainfall, storms, and flooding. And so that's where I want to take a journey with you today. And someone mentioned Tom Mode. I want to kind of set the stage for this so what factor that I talk about in my work. And I think it was, I don't remember, I think it's Tracy actually. One of the things that we did in this study, Tom Mode and I, we looked at Georgia's water supply, because in North Georgia, and oh, by the way, there's something going on in the country right now where the state of Georgia is very much at play. So I'm sure some of you are paying attention to it today. But in North Georgia, we get our water from surface water, from lakes and reservoirs and rivers. These are proposed and current reservoirs in North Georgia. What I placed in this box is something that you're going to notice a bit later in my talk. This is an area where we know that in the warm season, Atlanta gets more rainfall, North Georgia, because of the city of Atlanta. This is a downwind rainfall anomaly. And the point we were making here is that if we know this, why can't we use that science information to put more of our reservoirs there? So we can use that climate information in a hydrometeorological and a water resources fashion. And I think there are other places where our work is relevant too. So let's kind of zoom out and take a big picture look at what's going on here. We know that over half of the world's population is urban, over 50%. And I think by the year 2030 or so, that may be closer to 60%. We see that globally. If we look at the difference between 2000 and 2010, we see it in the United States. Look at the population change. I mean, this is really fascinating, because if you look at what's going on with the election right now, a lot of what's driving the votes are in those urban areas. So we see that urbanization is happening in our country, and that's also driven by population. So urban land cover, urban related air pollution, and so forth is increasing. So I'm in a geography department. My degrees are not in geography, but I do work that's inherently geographic. My degrees are in meteorology from Florida State, but we have to talk and think about scale as people that think about geography, right? And so when we think about the impacts and interaction of urbanization, it's a two-way street. from the urban, local, regional, or global scale, and then back down from the global scale to the urban scale. When we think about larger scale climate changes and how they scale down or downscale to the regional, local, and urban space. So in quite a few of the problems that I think about, I'm thinking about both of these directions oftentimes if you look at my research or read some of my papers. So I wanted to set that context. So what am I talking about today? I'm talking about the urban effects on hydrometeorological weather through the lens of observations and modeling. But I'm also going to talk about the broader impacts to society, risk, and vulnerability. And what you see there in this image is a satellite view and a thermal view from an aircraft of the Atlanta urban area and the central business district and the associated urban heat island. Those red, orange areas are warmer surface temperatures. And if you look on the top, you can see that those correlate quite nicely to the urbanization and road corridors around Atlanta. So that's well studied. When people think about urban climate, often the first thing they say is, oh, you study the urban heat island. And I was like, well, yeah, I've written some papers on that, but that's not really what I do. But I have to defer to this classic figure by Tim Oak and colleagues, because it allows us to understand some things about how an urban environment, whether it's Newark or Dover or Wilmington, how that urban space can communicate with the atmosphere above it. So this is a very classic paper that looks at the urban environment from different scales. It looks at something called the boundary layer, which is that first 1 kilometer or so above the surface, where the surface actually is communicating with the atmosphere. And we know that there are some really different things that happen in an urban boundary layer than a rural boundary layer. And so just keep those things in your mind as we move forward. The other contextual sort of aspect that I'd like to present before we really get into the heart of the talk is this framework that I like to use when I'm thinking about some of my research as well. This is actually something that I included in an SRN proposal to the National Science Foundation a few years ago. And it frames or quantifies risk as this function of the hazard, exposure, vulnerability, and resilience. So when we think about hazards, it could be a heat island, it could be a heat wave, it could be Hurricane Michael, a flood. That is the hazard. People are exposed to the hazard, people are vulnerable or sensitive to the hazard, and people have some degree of risk or resilience or adaptive capacity. So if you think about a snowstorm there in Delaware, that's the hazard. Now, who's exposed to it? There are people all across your region that are exposed to it, the cities, rural areas. But there's some people that are more vulnerable to that exposure, and there's some people that have less resiliency to bounce back from that exposure. And so all of that, from my lens, defines risk. And it's building on work by Brooks 2003 and the World Risk Report in 2013. So let's talk about risk. Let's talk about urban storms. Isn't that just a gorgeous storm? I'm a weather geek, so I think storms are gorgeous. I don't have I probably have, you talk to my wife, she probably does think I have a problem, because I run and look at storms when they approach our home, not run away from them. And don't do that, it's quite dangerous, but I'm very safe about it. But that's a storm that's not caused by the city. I just thought it was a cool picture, so I was included in my talks. Let's look at this radar image on my phone. Note, just stare at this for a few seconds. See that radar echo? That's a thunderstorm that popped up right over the city of Atlanta. Atlanta caused that thunderstorm. There was no large scale weather in the area that day, no fronts, no boundaries of any kind. The city of Atlanta caused that thunderstorm. Let's look at this one. We get to play meteorologist here. I'm a meteorologist by degree. In this case, you have a thunderstorm that's moving from the northeast into Atlanta. You can see that circular region, that's I-285, that's our version of a beltway. And watch what happens. You have a thunderstorm, you're gonna see this arc feature. You see it moving southwest, that arc line, that's an outflow boundary from the cold air from the rain evaporating. Watch what happens over Atlanta. Boom! It initiates new convection, new thunderstorms. So this outflow boundary is interacting with the city of Atlanta and perhaps its buildings to create new thunderstorms. Here's a case from Minneapolis sent to me by Kenny Blumenfeld. Some of you may know him, a geographer. And this is a case where you had a line of thunderstorms already in existence, a squall line. But as that squall line moved through Minneapolis, boom, it was enhanced. So these are examples of where either the urban environments are either interacting with or initiating new storms or enhancing pre-existing storms. Now, this is not a new concept. I got interested in it by looking at, and some of the sort of people that have been around for a while in the audience may have heard of something called Project Metromex. Stan Chagnon and his colleagues put sort of instruments and radars all around St. Louis back in the 70s and early 80s to try to get at whether some of Horton and Landsberg's early theories about urban environments impacting and downwind rainfall were true. And they came out with several publications that were published in the Bulletin of the AMS and various other places. But there was this geographer named William Lowry who published a paper in 1998 that said, hold up, wait a minute. There are some flaws in that work. Lowry said and issued these guidelines for that type of work. He said, if you're going to try to determine if an urban environment is impacting weather and climate, particularly rainstorms, you've got to have designed experiments with legitimate controls and stratification schemes. You've got to be able to replicate that experiment in several cities, not just St. Louis. You've got to be able to use spatially small and temporally short units reflecting the discontinuity of precipitation because it's very stochastic. And you've got to be able to disaggregate the climate data to increase sample size. So as a young scientist at NASA, I read this paper and I said, wait a minute. We just launched a satellite that I was working as a part of that mission called the Tropical Rainfall Measuring Mission, or TRIM, and that's it up in the right corner. I said, we just launched the satellite that specializes in measuring rainfall from space. So what that allows us to do is to take that rainfall data set and look at multiple cities. So I can check off one of Lowry's boxes here. I can replicate experiments in several urban areas. Instead of investing in one city with a field experiment, I can use data from the satellite and look at cities anywhere. And what we did, we published this paper in 2002 showing that indeed these rainfall anomalies existed downwind of these cities and over these cities. But I used satellite data. I didn't have to go and put instruments all around St. Louis or Houston or Dallas. Now that paper had some flaws, admittedly, because it was a very early satellite mission. We understood the weaknesses of the data, but we published several other papers afterwards with several of my graduate students with better techniques, radar data, et cetera. So for example, here's some work from Oklahoma City that we published with my first ever master's student that she actually followed me from NASA. She was doing an internship with me, came to UGA when I took the faculty position. So she looked at the Oklahoma Mesonet data, which is ground-based data, and she looked at data from satellite. And we found in the climatological downwind area of Oklahoma City, which would be the Northeast, it's Oklahoma City here, there was increased rainfall in terms of the Oklahoma Mesonet and also this rainfall factor, this factor that we use called the concentration factor. So in other words, don't worry about the methodology. We found that downwind of Oklahoma City, there was more rainfall. So we published that work in 2009. But then I started scouring the literature and placing our research within a broader context. And what I found is this wasn't isolated work. There's been work all across the globe on this urban rainfall effect. Now they've been doing it using some different techniques, but we were bringing in a completely new way of thinking about this using remote sensing, satellites, radar, and so forth. So I show this to make the point that our work is not in isolation. There's quite a bit of work sort of suggesting that there are urban effects on the hydrometeorological part of the cycle. So Karen Cito, a colleague of mine at Yale, and I wrote this paper in 2010. This is a paper where we were trying to essentially move people's thinking beyond the notion that urbanization is just manifested in the urban heat island. This is really kind of a summary or synopsis paper where we talked about all of the ways that urbanization affects climate. From the urban heat island, the clouds and precipitation, to surface hydrology, flooding, carbon cycle, and nitrogen cycle. So if you want a 101 on urbanization and climate, or if you're starting an urban climate course, I recommend this paper because it's a synopsis that is a good starting point. There are many others out there. Jamie Voigt and Tim Oak and others have a really good textbook out on this topic as well. So Tom Mote and I and one of his graduate students published, just to kind of give you some more examples of this urban rain effect, published this work looking at radar derived rainfall in Georgia. And I want to draw your attention to those dark green areas. That's the mountains. So we get a lot of rain in North Georgia mountains. We get quite a bit of rain in the southern part of the state and the coastal plain area. But look around Atlanta. Over Atlanta and downwind of Atlanta, there are these green areas too. Why not over here? It's the same climatological area region where this entire area should look the same in terms of rainfall character. But look, just over and downwind. That's a clue that something's different about what's going on over here. And so this is the urban rain effect that we're talking about. And it's not just in rain, you can see it in lightning. This is Tony Stalin's work. He's at the University of Kentucky. He looked at 8 years of warm season lightning flash counts. And look what you find. Over the city of Atlanta and just to the downwind. Same basic pattern as rainfall. So if you want to reduce your chances of being struck by lightning, you might want to buy a house on this side of Atlanta. No, seriously. If you want to harness the power of lightning in some way, you might want to put your lightning rods over here. So there's information in this data. One of our former graduate students, this is a really techie type, so I'm not going to spend a lot of time on a plot on, by Walker Ashley and colleagues. Walker's at Northern Illinois University, he got his doctorate at UGA. He also found, by looking at the total radar reflectivities, which is a metric that we use in radar, when it's above 40 dBz, that probably means there's a storm there. That's all that means. And he found some very interesting relationships between where the highest dBz values are relative to the distance from the city center. And that's all this chart is showing. This is a graphic from this. Let me just stop right here and say, this graphic got me in trouble with the Atlanta Braves baseball team. Let me pause for a second. They were really mad at me because of this graphic, the Atlanta Braves. Let me explain why. This is a paper we published in Urban Climate in 2018, Jordan McLeod and I. Jordan's down at the University of, well, somewhere in North Carolina now. And it basically shows you, using a much more robust data set, a longer time period, what I just showed you in the previous two, which is over and downwind of Atlanta, there's more rainfall. But I want you to pay attention to see this red square here? That right there at I-285 and Interstate 75, the Atlanta Braves built their new stadium, right in that red box. It used to be here. Now, a couple of years into their new stadium, the Atlanta Braves were noticing that they were having far more rain delays when they moved to their new stadium, which is here, not there. And so I tweeted, I said, oh, I could have told of that because they built their stadium in one of the anomaly regions where we know that there's more rainfall in the summertime. And so this reporter for Atlanta Magazine wrote this story based on our research and was kind of querying well, did you know that that's an Atlanta rainfall anomaly region? And why didn't you put a roof on your stadium and so forth and so on? So it was a really interesting back and forth for a while, but it's just science. And by the way, I want to make this point. This was in that same paper. The anomaly region in rainfall can move around. Now there's a climatological mean anomaly region that tends to be east of Atlanta, but under weak southerly flow out of the south, that downwind region is to your north. And so the rainfall responds accordingly. And so another contribution of this particular paper is identifying that this urban rainfall effect, the downwind anomaly, can move around. It's not just static. In the climatological sense, it's static, but it can move around. So that was really one of the, this is McLeod et al. 2018, this particular paper. And so my colleague Devin Yogi well, he was at Purdue, he just moved to University of Texas, has a really interesting summary paper, was recently published in Nature. And they took a lot of our research and others and synthesized them into sort of these prevailing thoughts on relative to a city where we have these anomaly regions and so forth. So that's what you're seeing there. So I encourage you all to take a look at Lou in Yogi, I think 2019. Okay, Dr. Shepard, some of you, some of this 100 and whatever, or 200 that are watching this, some of you like, okay, you've shown me some anecdotal or some observational or empirical evidence. Show me some modeling evidence. Okay, I got you. So models, you know, in meteorology and climate, we use these fluid dynamics essentially model. We model the fluid flow using Navier-Stokes equations, the equations of thermodynamics, conservation of momentum, and so forth. And we can model the atmospheric flow at different scales. But guess what else we can do with those models? We can take the atmospheric part of the model and couple it to the land. We can put a city in, we can take a city out, we can put a farmland in, a forest, and understand the impacts. And that's what we did in this study. Let me orient you to it, because I find sometimes academics, when we're talking to our own people, we are good at that. But when we're talking to broader audiences, we assume that people know what those little purple things are. You may not. So let me explain. So the purple that you see is cloud water. The little blue black arrows that you see is the low surface winds. And if you look carefully, you can see some yellow blobs. That's rain. So now let me explain what this is. Here's the radar image of the actual weather that day. This is Galveston Bay, and this is Houston area. We get sea breeze thunderstorms all along this coastline because of the sea breeze front. And I want you to pay attention to this cluster of thunderstorms here over Houston. Now, what we did with a model, on the left here, we removed the city of Houston. On the right, the city of Houston is included. What do you notice differently? When the city of Houston's not included in the model, you don't get that cluster of thunderstorms. When the city of Houston is included in the model, you do. So here's an example where we actually are using a weather model, a WRF-like model. This was the predecessor to the WRF model called MN5. And we have sort of established that the city of Houston was contributing as much to the causation of that thunderstorm in the same way those Atlanta ones were that I showed you earlier. Now, we took that a step further in this paper by my grad student, Michael Carter. Some people flew, and your geography department is geography and spatial sciences, so you'll appreciate this. People flew LIDAR or lasers over the city of Houston, and they were firing lasers down to get the urban canopy parameters, the height of the buildings, the roughness length, the mixing lengths, and so forth. And so we had that information, and so we embedded that into the urban model within the land surface model of our weather model. And so now we didn't just have this flat slab, we were actually representing the three-dimensionality of the urban morphology of the city, and we could see that there were different sort of wave patterns and rainfall patterns associated with the flow when cities were there and when cities were not there. Now let me come a little closer to Delaware. This is, I just, when I'm commuting to Athens from Gwinnett County, or when I'm laying in my bed or playing golf, I'm always thinking. So one day I started thinking, we often talk about urban heat islands. I think cities actually act as urban climate archipelagos. Now, an archipelago is a chain of islands. So my concept here, which we published in 2014 in IEEE Earthzine, was that when you have a chain of cities, they have an aggregate impact on the climate system that's different than an isolated. Think about a mountain versus a mountain range. A mountain might have sort of an effect on the flow and rain and temperature distributions, but a mountain range has an aggregate and a different scale effect. So we call these urban climate archipelagos. Now, in your area, you've got the Washington, D.C., Baltimore, up through your area, and Delaware, Philadelphia to New York. That is an urban climate archipelago. And that's how it's grown over the decades in your area. And so we ran studies where we modeled studies where we included that urban archipelago here and didn't include it for several different storms in your area, and the rainfall was different. So the urban spaces are indeed impacting not only the rainfall, it's impacting the heat island. Here's the heat signatures that are manifested through something in the model called sensible heat. So this is the urban minus no urban sensible heat. So you can see the little cities all along I-95 there manifested through heat along your urban climate archipelago. One final modeling study We published this in 2010 in a journal called Environment and Planning B. We took a day in the year 2005. It was the same weather day, so we took that weather day, but we grew Houston to what it was going to look like in the year 2025. This was, again, 15 years ago we wrote this, did the study. Working with the Houston Galveston Area Council, they used some agent-based modeling to grow the city of Houston. So you see the current Houston footprint versus 2025 Houston sprawl. And the character of the rainfall was very different. I changed the climate of Houston, not through CO2, which we know is happening, but because of changes in the urban land cover. I was able to change the rainfall climate of Houston. And so we know that's going to happen. Okay, so let's cut to the chase now. I've shown you observational evidence that cities affect rainfall. I've shown you modeling evidence. The burning question that some of you have is, okay, well, what's happening? Why does a city affect, initiate, or amplify convection? Well, we've summarized this in several of our papers, even some more recent papers than this, Shepard 2016 and so forth. So these are various chapters and papers. Four things we think are happening. One, atmospheric destabilization through enhanced thermal mixing due to low-level heating. In other words, because of the urban heat island, the air is destable, it wants to rise. That's one of the ingredients we need for precipitation and for cloud formation. So this little cartoon sort of gives you an example. Two, increased turbulence and mechanical mixing due to increased aerodynamic roughness created by the buildings in cities. So when wind blows across a wheat field in Kansas, it's going to stay straight. But if you blow wind through a canopy of trees, it's mechanical, it's mixing and turbulent, and there's convergence. Same thing with buildings. You need lift to get cloud development and rainfall. Thirdly, modified microphysical dynamic processes caused by the addition of aerosols from automobiles and industry. Now, if you've taken a basic weather course, you may know that every cloud on this planet has to have a little seed or nucleus, a condensation or ice nucleus to sort of nucleate that process. And so there's this thought that cities are rich in aerosols to serve as nuclei. And then finally, there's evidence that as storms approach cities, they bifurcate, split, and go around the cities. So these are all things that have been hypothesized that are as causes, but there's still some looseness in terms of the combination of which is happening when. So here's an example of this destabilization, the role of aerosols. Now, the role of aerosols is a bit unclear because there's some work that suggests that when you have dirty clouds, that actually causes the cloud droplet spectra or distribution to broaden. And so you get a lot of little tiny cloud drops that don't ever grow efficiently to become rain. So you don't get a lot of rain. But then there's another thought that, well, that can happen, but if you've got enough dynamic forcing from that heat island or from other things, you can eventually get those things lofted enough to form ice in larger droplets, and then they fall out as rain and you get more lightning. So the role of aerosols is somewhat unclear, still an area of very active research for any grad students that are out there listening that are looking for some research topics. All right, now here's one. I'm going to ask you a question. It's going to be a little bit weird. How do you like your snow, pork or beef flavored? And you're like, what is he talking about? Okay, I'll explain. This, I was so fascinated by this. I grabbed my my phone and started recording the radar. This is a plume of snow just downwind of Dodge City, Kansas. You guys see that little plume? That's snow. Here's a satellite image the next day showing that on the ground. That's actually a satellite image showing the snow footprint. Tom Mote and I wrote a little summary paper of what was going on here. The National Weather Service Dodge City actually documented a localized downwind snow event attributed to animal slaughterhouses and power plants. All right, let's break this down meteorologically. So the power plants were providing a source of moisture and perhaps some aerosol. Perhaps the slaughter plants were also providing moisture and aerosol. So under this prevailing wind flow from the southeast, we were getting enough convergence and seeding of the clouds that we just got this little plume of snow right there. And so this is an example of the sort of aerosol effects that you can have on precipitation. And then here's the bifurcation effect. My colleague Bob Bornstein and others have done work here. Here's an example that he showed where you get this happening where you have a large thunderstorm, in this case approaching New York, it splits into two smaller branches. Now the question is this a thermodynamic effect or is it a barrier effect of the city? I think there's active research. I have a hypothesis that it's von Karman eddies. I haven't tested this hypothesis, but I've seen some examples in some of my own modeling work that make me sort of curious. Now, if you don't know what von Karman eddies are, this is a satellite image out over the Pacific Ocean. This is a volcanic mountainous island. We see this all the time. Now, the mountain is there. The flow is coming from the northwest, coming that way. It impinges upon the mountain, and you get these von Karman eddies downstream. That's basic fluid dynamics. I think cities do something similar. I haven't proven it, but that's my hypothesis. So one day, I'll write a grant to NSF or something and try to test that, or someone will if they hear this, but that's my hypothesis. Okay, so let's kind of transition to the third part of this talk. I had a first part of the talk gave you the broader context. The second part of the talk talked about the urban rain effect and the evidence for it. Now I want to talk about other risks, because remember the framework I always operate from is risk, other risks associated with urban precipitation. So let's talk about urban floods. For those of you that have been in Atlanta, this is Six Flags over Georgia. I think there's one up that way somewhere near New Jersey. One in Maryland too, actually. This is not a new water ride at Six Flags. The entire park flooded in 2009 because of a major 500-year flood event. And one of the things that we know is that your fourth grade curriculum lied to you. Why do I say that? Because when we were all in fourth grade or third grade or wherever we were, we learned about the water cycle, right? The evaporation, condensation, runoff, precipitation. But all water cycles aren't natural. The water cycle in a city is very different than the water cycle in a natural environment. Because in a city, because of the pavement and parking lots, you have less infiltration into the soil and you have much more runoff because of those impervious surfaces. So there is an urban water cycle and there's a natural water cycle. And there also are parts of the urban water cycle, which I teach about in my urban climate class, the piped in water, the human sources of water as well. So you can also add that into the urban water cycle. So because of that, if we look at this hydrograph, which is a graph of runoff versus time, what we typically see is that developed land that has Target and Walmart parking lots and paved roadways, is going to have a much higher peakedness in terms of its runoff response than natural landscapes. So you couple higher rainfall or more intense rainfall rates that we're seeing because of climate change. You couple that with more impervious surfaces and a stormwater management system that is designed in cities for the 1970s rainstorms, not the 2020 rainstorms, and you get more urban flooding. That's what's happening. So Neil Debbage and I published this paper in 2018. This is some of Neil's doctoral work. And what we found in Atlanta, Charlotte, Greenville, South Carolina, is that more urbanized watersheds exhibit a greater number of high and low threshold exceedances, as well as larger peak unit discharge. What that basically says is where you've got more urbanized landscape, you get more flashiness to the floods. You're more likely to flood. And oh, by the way, I didn't include it in this talk. The third part of his dissertation, we talk about some of these equity issues. We found that in the Atlanta, the Greenville, the Charlotte, North Carolina I-85 corridor, African Americans are about 60 to 80% more likely to live in flood-prone areas. So there are equity issues at play here that we need to deal with going forward as well when we use some of this climate knowledge. This was the 2009 flood event in Atlanta that I talked to you about. In another paper that Neil and I worked on, we ran models and we found that flooding, even though it was caused by a larger scale synoptic weather event, a cutoff low that was stuck to our west for a week, we did find that the rainfall was enhanced or amplified by the presence of the urban surface. So that urban rainfall effect that I talked to you about earlier was embedded in the overall larger scale weather system. And so you got these little anomaly regions. See them, those little areas of enhanced rain. So there was an amplification within the broader weather system that was causing the flood. And so this was a really pioneering study, because most of the work has been looking at isolated or warm season convection. People have sort of shied away at trying to understand how urban effects of rainfall are embedded within larger scale weather. So we were really proud of that paper. Neil Debbage is now a professor at University of Texas, San Antonio. And oh, by the way, because you live in a place that gets much more winter precipitation than I do here in Atlanta, my former PhD, Brad Johnson, who's now a faculty member at the Florida State University, he looked at the mixed precipitation events in your region, up in that I-95 corridor from DC up to New York. And what he found is that when the wind events were relatively light, the urban heat island remains intact more. What that does is, so when you have these wintertime precipitation events that you all experience, you're less likely to get freezing rain, because freezing rain is the rain that falls to the surface and then freezes when the temperature is below freezing. And so what Brad found is, in his sort of 2-decade-long study, is that there are cases where the urban areas have less occurrences of freezing rain because their temperature stays just above freezing because of the urban heat island. So this was our attempt to move some of this work into the frozen or freezing precipitation regime. I'm going to skip past that because I want to get to this. I already kind of talked about that a little bit. So Dev Niyogi, Bob Bornstein, Sue Gramond, and I, very well-known folks in this area, we've been trying to conceptualize all of this, because right now we know a lot of things that are happening, but we don't really know how to conceptualize it for forecasting. We've got to understand what happens under different synoptic scenarios: calm conditions, strong urban heat island, weak urban heat island. So this little block diagram is my attempt, along with these colleagues, to put on the table all of the factors that need to be considered when we're thinking about understanding and predicting the urban rainfall and urban storm effects. So that's kind of a synopsis there. Yeah. So where we're headed, don't worry about the words here. I just wanted to point you to the fact that this is a series of research questions that were recently asked in a NASA-funded IDS proposal. We just got this funded this year as a $2 million project. I'm the lead PI, but it involves Maryland, Texas, Florida State, and who else? Auburn University and UT San Antonio and LSU. And if you look at the different sub-elements, sub-elements 1 are really dealing with understanding more about the character of urban initiated or enhanced storms. Sub-element 2, we'll be working with our colleagues at NASA to try to better understand and predict in the models these processes. And then sub-element 3 is more of a geographic spatial project, where we're going to develop an urban climate archipelago atlas based on remote sensing data and previous studies. And then finally, sub-element 4 really gets at more of a sort of fine-scale operational predictive capabilities. Will one day the National Weather Service office, you might look up there on your app and say, no large-scale weather systems today, but there will be urban-generated rainfall to the west of Dover, blah, blah, blah. That's kind of where that research element is headed. So in closing, I wrote, along with several colleagues, I was involved in this National Academy's urban meteorology. There was a study workshop, and I was included in that. And the academies wanted to know, because this was a growing area, how can we make actionable what we know about urban meteorology and urban weather and climate? So I encourage you, if you're really interested more in this topic, this is a free download, I think. It's a couple of years old now, but it has some really interesting information on how we can make information actionable. So in my final thoughts, urban environments modify precipitation. When I got into this, that was still an open question. It's conclusive now. And I think a lot of our work has helped make it conclusive, frankly. Urban environments and broader climate change are likely increasing flood hazards. Urban hydrometeorological processes have useful information for planners, water managers, engineers, and policymakers. And discussions of urban mitigation strategies need to consider the implications of precipitation, flooding, storms, in addition to just the urban heat island. And then finally, how do we talk more to people that need this information? I still think we're bad at this as scientists. We have all of this information over here in the academic and ivory tower world, and you have the practitioners over here. They don't read our journals. So what is the interface to make this actionable? That's an area that I've increasingly been thinking about as well. So I want to stop there and thank you all for, again, for having me as your Mather lecturer. And I'll, I guess, take some questions.
Well, that's wonderful, Marshall. Thank you so much. For those of us in the weather and climate, we geeked out with all the different studies and things that you're doing. So we do have questions in the chat. So if you don't mind, I'm going to ask you a couple of those and we'll watch our time. Jack Gardner says, has there been any before and after studies of new urbanizations in sparsely settled areas like Brasilia?
Jack, that's a really interesting question. That particular city in general is one that I've actually wanted to look at because of what you mentioned about the sort of new urbanization. I think when we have these new emerging urban spaces like that, or in Dubai and other places, they offer natural experiments for us. I personally have not done. There has been some limited work on urban rainfall in South America, but South America is certainly an understudied area in this region, but one that we actually are addressing in this new NASA IDS proposal. My colleague Chandana Mitra at Auburn is going to be looking at some of these understudied sort of continental regions from the perspective of, so Brasilia is, I've looked at Brasilia and the geography and topography around it is perfect for this type of study, because you want to choose cities that don't have, if possible, don't have sort of topographic or coastal related influences. Although there are some cases where we want to understand those interactions too. So that's a great question.
So Heng Chen Ye has a question for us and says, does the more precipitation in certain parts of a city reflect longer rainfall duration, more rainy days, or higher intensity, or all of them?
So in the paper that I mentioned, the McLeod et al. 2018, Heng Chen, we found that it may be because they're more convective, there's higher intensity, but I think it is a combination of both. I think it's a combination of a frequency of occurrence in those specific regions, and it turns out that there's a bit more intensity in terms of the DBZ, or a convective nature of the storms as well.
Cicely Stepp says she has no question, but has a comment for you. Mm-hmm. And I just lost a second because another question went in.
I see it.
But considering the three-dimensional nature of Houston model, in terms of Houston in a model, is so cool. She says, I'm biased from living in Houston and working as a lifeguard for a few years. Predictable, 1,530 thunderstorms.
No, yeah, very interesting place. It's very convective, and it's also, Houston's a poster child for sprawl too. So it's a very good city for studying this topic.
So Del Levia has a question. He says, superb talk. I ditto that. Can you speak to the extent to which green infrastructure in cities mitigate storm water runoff? So has there been more trees planted in Atlanta that have an effect in terms of reducing the magnitude of floods in something like that you showed with Six Flags, or, made smaller flooding episodes?
Now, Del, that's an excellent question. I actually volunteer for an organization in Atlanta called Trees Atlanta, where we plant trees around Atlanta and do other greenscaping activities. But to be candid, it is done primarily from the heat island mitigation standpoint, not the flood runoff mitigation standpoint. There is an effort ongoing right now, Del, at UGA, where I'm sure, like everyone else, there's a new NSF Sustainable Regional Systems call from the NSF, $12-14 million project. And we are thinking carefully about sort of engineering with nature-based solutions in urban spaces for runoff issues. So we haven't done much work in that area, but we're thinking about it. So thank you for the question.
So Jen Crotty Roth is one of our graduate students, has popped in. She says, hi there, thanks so much for your talk. Here's my question. If the cities and areas just downwind of cities are seeing enhanced rainfall, have you noticed if the areas downwind of them are seeing less than normal rainfall? Are the cities acting like cloud seeders and stealing the rain from their exurbs?
That's a question that I often get after giving this talk. I think there is, and there are even some ethical parts of that too. There are ethical issues that come up with cloud seeding in general. Are you stealing rain from someone else when you seed a cloud, for example? That same question comes up because as I showed you in many of those maps that I showed, there's certainly areas that are anomalously less. It's an interesting question. I never really have a good answer for it because I haven't quite figured out a way to quantify it. I mean, I guess we could do some budget studies, and I actually thought I had a student that was going to come and do that for me as a part of a research project, but then we ended up getting a grant funded and I needed her on a different project, to be honest with you. So I think there's still there's a master's dissertation in there somewhere to do a budget study to understand sort of the inputs and outputs from these sort of adjacent regions. We just haven't done them.
So another one from one of our current graduate students and also a staff member here says, first, thanks for your social media work. My question, with global warming and thickening of the atmosphere and with the reductions in aerosols and better green infrastructure, will urban areas have a larger or less impact on convection in the future?
Great question. One of the things I've been trying to kind of, been crying in the wilderness about, if you will, is we can't ignore the role of cities on climate. For example, we can lower the temperature of Newark or Atlanta or Athens, Georgia, very quickly and easily using mitigation techniques at the local scale that have nothing to do with greenhouse emissions. And so in the same way that we can have almost an immediate impact on the temperature or perhaps even convective scale, I think we also have to keep in mind that cities are going to be cauldrons for climate change. Not just from a rainfall or hydrometeorological perspective, but when you have a heat wave and then you have the additive effect of the urban heat island, urban dwellers are suffering that much more. I mean, everyone's exposed to the heat island, but there's a greater level of sensitivity or vulnerability in the cities because you've got the additive effect. So that's at the local scale. But part of the reason that I kind of wrote that paper on urban climate archipelagos is that when you start to aggregate these individual cities into these megalopoli, I think they start to have an influence at the regional to the larger climate scales. And so that's why I was trying to raise the flag or sound the warning levels about these emerging megalopoli all over the world.
So this is from Clint Rowe. This will take us back. He says, Marshall, this is Clint Rowe from the University of Nebraska. It's a great thing about being able to do something like this online. He says, thanks for a great talk this evening. I'm teaching boundary layer meteorology this semester and will now have to make some changes in my urban boundary layer lecture next week. I'm intrigued by your comparison of the storm bifurcation and the von Karman vortices. Do those vortices contribute to the enhancement of precipitation?
And that's why, and thank you so much for joining in from Nebraska. My colleague Tom Moat will be thrilled to hear about it. Tom's has Nebraska roots too. I'm good friends out there with Ken Dewey, so say hello to all those folks. I think they do. I think that's I think the bifurcation is there, but I really want to do a modeling study where we just try to first identify that von Karman flow is there. And I'm not in a vacuum here. I've seen some evidence of it in some of Michael Carter's thesis work. There were these little vorticity streamers somewhat downwind of the urban area, and that's what gave me the idea. But I think there is a possibility that they could come back together and converge. And so that might be part of the downwind signal too, not just the urban heat island circulation or the drifting downwind from the urban. Again, I think it's tied up in there. I just haven't proven it, but I think you're spot on with what you're thinking about. By the way, I didn't mention this, but one area that we're also going to be getting into with this new grant, when you remind me about boundary layer, I teach the mesoscale meteorology class at UGA. I'm really interested in what the differences are in certain convective parameters in an urban versus non-urban spaces. So for your meteorology, we're going to geek out here for a second. You probably heard of CAPE, convective available potential energy, but there's something called surface-based CAPE, and there are other parameters that are very much tied to the surface layer, the canopy or boundary layer. We're going to really sort of look at sort of what the sort of climatology of some of these surface-based convective parameters are in urban versus non-urban spaces.
So let's squeeze in one more question for you, Marshall. It's from Dan Leathers,
Hey,
colleague in geography. He says, wonderful talk, Marshall. We're looking at winter precipitation and cities, especially at snow in urban areas compared to rural areas. Has there been much work done in terms of looking at winter precipitation?
No, but Dan, I feel like we probably talked a little bit about this before. My colleague, my student Dan my student Brad Johnson published that one paper in Urban Climate, but he was just looking at how sort of snow, mixed phase, and freezing rain systems were distributed. We do have one paper that we're still trying to get through the review process, sort of a modeling WRF type paper. But I think, Dan, that it is a rich area for study. So if you have some people there interested, there is not very much done on sort of, I think the two areas that are sort of emerging are urban impacts on winter precip and urban impacts on convective storms and tornadic storms. And a third area too, urban impacts on landfalling hurricanes. There have been a couple of studies out recently showing the enhancement of rainfall and hurricanes as they make landfall.
All right, well, thank you. So there's a couple questions we didn't get to. So Marshall, I'm gonna ask if they can send those your way if you don't
Sure.
mind. And
Sure.
we do want to kind of stay on time because we have some time slotted for Marshall, Dr. Shepard to talk with the grad students. But in closing, I want to thank you. This was a wonderful talk.
Okay, can I quickly, I'm sorry. I wanted to, Abdullati asked a question I can quickly answer, bridging the gap between communication and researchers. Read my paper in Forbes, 9 tips for communicating science to people who aren't scientists.
So that's one of the grad students. So you may get a chance to talk with him too.
Okay.
But I appreciate that's nice of you to kind of jump in. I wanted to just real quickly thank those who work behind the scenes to make this happen. April English, Mark Jolly, and Sandy Raymond, we thank you. All those of you in attendance, it's just wonderful for you guys taking the time out of your evening, because I know we get zoomed out, and it's really nice that you could join us back for an evening talk. I also want to say one more time, thank you to Sandy Mather for making this event possible. We look forward to continue the memory of Russ Mather as we go forward next year, and hopefully that will be in person. So that concludes the evening. Thank you so much.